the high-speed interface IP validation based on Virtual Emulation Platform. Abstract. As the complexity and the speed of HSI, high-speed interface IPs are rapidly increasing with every generation. It's becoming harder to functionally validate the HSI IPs within given schedules. To achieve this, various methodologies are utilized to completely validate the ASI IP. One of the commonly used methods is the field programmable gate array (FPGA). However, using the FPGA is still has some challenges such as visibility, high effort to implement design, and high turnaround time (TAT). This paper suggests Virtual Emulation Platform to address the above problem. The Virtual Platform is to use to test the design under task (DUT) with OS level applications on a virtual machine, and has the advantages for full-blown emulation like full visibility and real scenarios and fast speed. 1. Introduction. The current electronic devices require large data storage to store numerous data and perform necessary calculations quickly. Most of them can communicate with other devices through various interfaces instead of standalone communication. This requirement of the high speeds leads to wide usage of HSI IPs in modern mobile application processor AP designs. The recent trend has been HSI IPs being widely used in various system-on-a-chip (SoC) products such as automotive, artificial intelligence (AI), high-performance computing (HPC), and Internet of Things (IoT) devices. Therefore, to design competitive SoC, the HSI IP needs the completely validated prior to SoC design, as the complexity and the speed of HSI are rapidly increasing with every generation. It becomes harder to completely validate it up to the functionality within a project schedule. Traditionally, FPGA is commonly used for HSI IP validation. However, FPGA inherently has a challenge to achieve the real speed of HSI IP. Also, FPGA-based validation platform requires a complete implementation of the design and additional multi-project wafer MPW test chips, including analog circuitry of physical layer for HSI validation. We can start doing the functionality validation in parallel with the developing software, cause only once MPW test chips are physically available. Those problems become the main bottlenecks for HSI IP validation in terms of project schedule and quality of product. This paper suggests the Virtual Emulation Platform (VEP) to address the above problems. The concept of virtual emulation is to connect a hardware emulator and the virtual machine using virtual interface and test DUT with the specific application on a virtual machine. VEP can be used at a pre-silicon stage, and it can develop a target software code and make the functional validation with the OS level scenarios by leveraging proven device driver pruning on the virtual machine. In this work, we demonstrate that VEP approach can reduced TAT by 33.3% and achieved 19.7% higher functional coverage compared to the traditional method. 2. The concept of virtual emulation. Emulation is widely used for the system-level validation of modern SoC design at a pre-silicon stage. Many companies validate their SoC using emulation with firmware. By extension, with a specific application like DaeSeo DOU scenario. However, one of the biggest challenges of the IP level validation is how to take tests with more realistic scenarios such as OS level application with the device driver over that IP. The virtual emulation technology is targeted for the above challenges and needs a software adapter that enables user application and OS drivers to establish a virtual protocol connection to the hardware emulator. Figure 1 shows the concept of the virtual emulation, and the red box indicates the software adapter, which is the key solution of the virtual emulation technology. The Figure 1 concept of the virtual emulation. The Figure 2 shows the detailed architecture of the software adapter. The software adapter means the combination of the DEV1 and DEV2 on the left hand side and DVE1 and DVE2 on the right hand side. An application in virtual machine is used to the interaction with the driver to open the concerned virtual device and the stream in the protocol transactions. And the driver, which is proven in the OS, communicate with the virtual device that is not an actual hardware, but a virtual prototype. The DEV1 and DEV2 on the left-hand side are called the driver adapter as specified in Figure 1. This driver adapter intercepts the transactions going to the virtual device and sends the data as packet to the device 1 and device 2 on the right-hand side. The protocol transactor is composed of DEV1 and DEV2 and C proxy interface transactor, and it connects via the protocol to the DUT in the hardware emulator. The Figure 2 virtual emulation software adapter architecture. 3. High-speed interface IP validation flow. A. Existing HSI IP validation flow. The Figure 3 shows an example of a ASI IP validation flow based on FPGA with the MPW platform. The platform is configured with the mini SoC having a PCIe link controller on the FPGA side and a physical layer in the MPW test chip. The mini SoC is optimized for executing target software code for HSI IP and consists of an ARM CPU, a system interconnect, memory, and prefers like UART interface for software debugging. The physical media attachment sublayer PMA and PHY has many analog circuits and hence PHY is provided a separate MPW test chip connected through a physical coding sublayer PCS and PMA interface with FPGA. For validating PCIe endpoint with this platform, back-to-back connection is required. This means that through the back-to-back connection, checking compatibility of PCIe protocol is impossible. In this approach, an MPW test chip has to be fabricated and it usually takes about 10 weeks which is critical to meet a time-to-market requirement. In the meantime, simulations can be used to partially replace the method. However, it cannot manipulate all of the features due to the speed limitation of a simulation. Although the platform has difficulty in achieving the full speed of a PCIe Gen3 by the nature of FPGA. The Figure 3 previous work FPGA with the MPW platform. B. Proposed HSI IP validation flow. The proposed VP also has a mini SoC on a hardware side and a virtual machine with a Linux OS including virtual device on the virtual side. Unlike the existing platform, the synthesizable 5 model covering the PMA is used instead of a MPW test chip, and it can communicate with the PCIe link controller. However, the synthesizable PHY cannot handle analog features like equalization or lane margining. Additionally, a protocol transactor is newly added in the hardware side for communicating with a virtual device through a virtual interface. Figure 4 shows the proposed VP for validating a PCIe Gen3 IP. Figure 4. Proposed work. Virtual emulation platform. The proposed BP has 3 advantages compared with the existing approach. BP does not require the MPW test chip. Thus, the BP enables us to develop the target software code early. Because the BP is available at a pre-silicon stage. In addition, we can efficiently make the software target code more robust by leveraging a real device driver on virtual machine. VP can reinforce the functional verification by performing the application on OS and accelerating the simulation speed using hardware emulator. Through the BP approach, we can test many of the scenarios of interest combined with inbound or outbound transactions, including massive data, power management, aging test, which cannot be achieved in simulation. 3. BP can measure the performance of the HSI IP in a real benchmark program such as Iometer with the full speed of a PCIe Gen3 IP. The existing platform cannot run at speed of the HSI and will always be slower than the target speed. However, BP has no such limitations and can learn the required speed of HSI IP. Due to this functionality, we can check whether it complies with the effective bandwidth of the PCI Express. Base specification revision 3.0, 8.0 giga transactions per sec. So in addition to the above advantages, BEP has flexibility to debug DUT and the software with a fully static environment, which means there are no timeout constraints. Thus, software engineers can freely stop the DUT whenever they want. Lastly, the BEP environment can be easily replicated to the other project, which enables us to shorten TAT of similar project. 4. Method to accelerate pre-silicon validation. When the VEP environment is ready, we can proceed with the functional validation and adopt the target software code to meet the hardware HSI speed. If the main purpose of the VEP is to validate our PCIe Gen3 IP, then the interface between the virtual machine and the DUT should use the serial interface through the physical layer. However, if the main purpose of the VP is software development, there is another method to accelerate the emulation performance, which is detailed below. To accelerate the emulation performance, using the pipe interface for PCI Express interface has been chosen. The pipe interface is intended to enable the development of functionality equivalence PCI Express PHYs. The pipe specification defines a set of pipe functions which must be incorporated in a pipe compliant PHY, and it defines the standard interface between the such PHY and link layer of the PCI Express. With the serialization and deserialization status pipe. Thus, the pipe interface uses parallel data transaction instead of a serial interface using TX-RX channel. With a real speed of HSI IP over 5 Gbps, runtime performance of emulation is degraded because the emulator is capturing event at every clock cycle. Using a fast clock inevitably causes capturing a lot of events, and in case of PCIe Gen3 IP, the serial interface uses a clock frequency of 8 GHz, whereas the pipe interface uses a clock frequency of 250 MHz. When the data width is 32-bit, that means the serial interface captured 32 times more than compared to the pipe interface. The longer the scenarios, the cap of the frequency makes the huge difference on their runtime performance of emulation. Figure 5 shows the VP with the pipe interface. Figure 5, Virtual Emulation Platform with a pipe interface. Therefore, the paper suggested the mixed interface methodology for software development. The first step is integrating the pipe transactor instead of a PCIe PHY transactor. Using the pipe interface does not require the synthesizable PHY model. This means building a VP is faster using the pipe interface compared to the serial scenario. This makes it possible to develop basic firmware and device driver. After the software is ready, synthesizable PHY and model and PCIe PHY transactor are integrated to the VP to validate the IP with the developed software, including massive data transaction and power aging test. This methodology effectively enables us to reduce the TAT for HSI IP validation. So the figure 6 shows the overall flow of the mixed interface methodology. This approach requires higher engineering effort. For using mixed interface methodology, two emulation environments are required for validation. One is the DUT with a pipe transactor, and the other is DUT with a pipe transactor, so that the integrating method is different in its own environment. Figure 6 is a mixed interface flow. Table 1 compares the performance for PCIe Gen3 link-up and loading the VM virtual machine with the 5096 transactions according to the type of interface. Regarding the scenario for the PCIe Gen3 link-up, as we estimated the above, the results show the pipe interface reduced the simulation time by a factor of 31.35 times compared to the serial interface. The word clock time performs even faster than estimating. It can be helpful for debugging the link equalization process during the link-up at generation 3 speed. As well as testing the base functions, developing the firmware. Even if the reduction ratio of 4096 burst transaction-driven virtual machine is decreased in comparison with the Gen 3 link-up. It's acceptable because the bottleneck is loading the OS in a virtual machine and not related to hardware. Table 1. Performance comparison. 5. How to debug in a virtual emulation platform. The VEP methodology has different debug methods based on type of error, protocol error, data error, which help to ease the difficulty task of the developing target software or debugging complex IP. To analyze the protocol level transaction, the VEP can use log files generated by the socket on the server side. The log file bombs transaction layer packet TLP information of the data, which contain the type of transaction, address length, and data header field of the TLP. Thus, software engineers can use the TLP information for debugging their code with a software debugger virtually connected to the hardware emulator through the virtual joint test action group JTAG interface. Figure 7. Software debugging method. For hardware engineers, the VEP records all the transactions flowing between the virtual machine and the DOT using CSV format, both of the server and client side. The CSV file has a type of transaction such as configuration, read, write, and address data of transaction with a timestamp. The timestamp helps the hardware engineer to locate points of interest of the waveform and also easily dump waveforms at the speed point of interest. Figure 8. Hardware debugging method. 6. Results. The proposed VEP was applied to a validation of the latest PCIe Gen3 IP. We were able to achieve 19.7% coverage increase and a 33.30% TAT reduction. Table to show the coverage comparison between the previous platform and the proposed VEP. The previous platform covered only 68.1% of a total validated space because it had many limitations to exercise all the PCIe Gen3 features. This meant that we had to verify the other features with the simulation. But the VEP can almost cover the PCIe Gen3 features and its coverage up to 87.8%. The remaining area is an analog characteristics like link equalization and lane margining, which the VEP cannot access. It can be only covered by the platform which uses FPGAs and MPW. Table 2. Coverage of PCIe Gen3 IP validation. The figure 9 shows the achieved coverage and time according to the platforms. By proposed approach is that both simulation and simulation acceleration were used for sanity checking in the beginning, and the VEP was used for early software development and validation for 6 weeks. Finally, FPGA with the MPW platform was applied to validate the remaining features with the target software code proven the VEP with the OS level scenarios. As a result, we were able to successfully demonstrate 33.3% DAT reduction by relying on a VEP. The figure 9 is time and coverage of each platform. 5. Conclusion and future work. An innovative VEP virtual platform emulation platform methodology is proposed for validation of high-speed interface IPs in this paper and successfully demonstrated the achievement for all desired objectives. Using the proposed approach enables us to develop target software codes and take OS level tests with the full speed of HSI IP at the pre-silicon stage. Through the validation of PCIe Gen3 IP, the VEP significantly improved finding design issues at the early stage and achieved a higher functional coverage up to 87.8%. So furthermore, it is expected to reduce the TAT of HSI validation using the VEP. VEP has unique benefits such as flexibility, debug capability with a static environment, and accessibility at early stage. This approach will be complementary approach with the using in-circuit emulation. In-circuit emulation can achieve the high performance test with a real board level environment. By combining those two solutions at each of the design stage, it is expected to greatly improve the ease of designing higher quality and error-free products. This proposed solution using VEP is still at the beginning stage to validate HSI IP. Many HSI IPs are required to verify their analog characteristics like equalization and lane margining in the validation stage. Therefore, functional verification and validation are focused on the simulation stage before silicon. However, the simulation cannot cover long test scenarios such as massive data transaction and power aging test because of simulation speed. If a functional error occurs in silicon, an engineering change order ECO is required, but it's not easy to find whether the error caused by hardware or software. By using VEP, the problem will be handled at the pre-silicon stage and error in silicon can be debugged. Can be. Many engineers have depended on silicon or FPGA for HSI validation, but if the technology is utilized, VP can solve most of their concerns at the early stage. Even though this solution handles functional validation, it cannot handle analog characteristics of the IP, which is also an important metric. Handles if the emulation environment can provide the analog handling technique or modeling, the tools can be even more powerful. They improve coverage to almost 100%. To make this impossible, close collaboration between the electronic design automation, IT vendors, and industry is required, which can be the subject of future research on this area. Reference. Thank you for your time. Today, I read the high-speed interface IP validation based on Virtual Emulation Platform was published in the DVCon2019. Thank you again.